Hello everyone, my name is Sagar Sapota. I'm an integrated PhD student at Kangon University in the Department of Electronics Engineering. So today I'm going to present on introduction of MMIC technology. So without further delay, let's begin. The content of the presentation are review of MMIC technology, materials and device of MMIC, and all the MMIC active devices, and fourth, MMIC passive devices, and last summary. Let's talk about the review of MMIC technology. MMIC stands monolithic microwave integrated circuit. It's like a type of IC which is mainly operated at a microwave frequency, which can range from 1 GHz to 100 GHz. And MMIC are used as an amplifier and filter in communication, radar, and RF and biosensing system with high frequency, high performance, low power consumption, and also highly rare utmost requirements. So you can see like in radar and wireless communication, this IC MMIC is widely used. So talking about the history of MMIC, and the trace of MMIC can be traced back to 1964 at Texas Instruments, where silicon MMIC switches, mixers, IF amplifier, and phase shifter were developed, which has a common root with MMIC technology, but the IC weren't good performance at the time. So in 1988, there is a breakthrough in silicon, where ARFA launches a massive research and development program, which performance was excellent and lead to common application such as DVSP TV, ACSR, and wireless. And talking about MMIC versus hybrid MMIC, this table shows a comparison between MMIC and hybrid MMIC in terms of size, cost, productivity, reliability, and performance. Talking about MMIC, it's non-redundant engineering. The cost is very high. NRE cost is very high for MMIC, and for hybrid MMIC case, NRC cost is very low. So, and on MMIC, size and weight are very small compared to hybrid MMIC. And mass production cost is very low for MMIC, but for hybrid MMIC, mass production cost is very high. For MMIC, very good design flexibility and also reliability, good broadband performance, and high level of integration is possible, and also reproductibility and reliability are excellent. But in case of hybrid MMIC, limitation in broadband performance, high level of integration is possible. Reproducibility and reliability is fair to good with, and also good repairability. So talking about application field of MMIC, the table shows different type of application in different fields. In military sectors, it can be just adaptive phase radar, smart mutation and decoys, and also electronic warfare, and also remote sensing and altimeters. And in space sector, it can be used as satellite TV receiver, evolved phased array antenna, and radiometers and astronomical field. And in terms of civil sector, satellite TV receiver, and MCAT wireless communication, and fiber optical systems, LAN, etc. It also uses Bluetooth and high-speed internet. So the major foundries of MMICs are, let's see in the table, the different manufacturing foundries company. It's a semiconductor foundry is generally a semiconductor manufacturer whose business is focused on fabricating chip for third parties. It ships whole fully processed semiconductor wafer but not packaged chip. You can see the table list of gallium arsenic, silicon, and silicon carbon substrate foundries. Like process, you can see gallium arsenic, gallium nitrate, and the fabrication companies are Element, Motorola, Fujitsu, Toshiba, Hitachi, Samsung, and Alpha Technology. For silicon, Element, Analog, Emerald, Complex, and Harris. And also material used in MMIC are the most common used in MMIC are group third B compound, which is gallium arsenide, indium phosphate, gallium phosphate, and aluminum gallium arsenic, and also group IV elements that are silicon compound and silicon germanium. You can see here the table depending upon the properties, different properties of different compound and element on electron mobility, resistivity, permittivity, thermal conductivity. Also wafer size, wafer cost, energy band gap, approximate process. Like we can see, electron mobility for silicon case is very high, like 15, and but in case of aluminum is more higher for gallium arsenic and germanium. It's 3,900, and also you can see here silicon germanium. It's range from 2,500 to 3,000, and like that. And you can see the electromobility is higher in gallium nitrate. Like in terms of resistivity, also we can compare different material depending on our application. We can choose which is the most suitable material for our application. Active devices of MMIC. The material choice for MMIC application is dependent on the electron drift saturation, velocity, mobility, and resistivity, among others. The main active device for MMIC are explained briefly in the following. Gallium arsenic MOSFET, gallium arsenic MOSFET devices are operating depletion mode, require negative voltage to control the gate. The advantage of gallium arsenic over silicon are its higher saturation, electron drift, velocity, lower the structure of gallium arsenide MOSFET, and its equivalent circuit are shown below. You can see the gallium arsenide MOSFET I see, like you can see source, it's a source, and between source and N-type layer there is only contact. This is gate, and here this drain, and then it's active layer, buffer layer. Same is insulating, it's a subset. Talking about silicon germanium SPT, silicon germanium diamond lattice structure, and the lattice see germanium is 4% better than the silicon lattice construct. The emitter has a wider band gap than the base, although the silicon germanium has a lower bandwidth with different lattice constant. The main structure, first generation, second generation, and third silicon germanium SPT and its band gap diagram are shown in figure. You can see figure. Then it's a schematic cross section of third the compound SPT. Also below one, you can see the schematic diagram of first generation silicon germanium SPT. So silicon BJT, the diagrams. The symmetric of a high performance silicon bipolar junction transistor is also called silicon BJT. BJT are fundamental electronic devices that amplify current. They are used in various applications, including amplifiers, switches, and voltage regulators. And you can see the figure. Diagram of high performance silicon BJT. Talking about passive device of MMIC. Passive device are the device that doesn't need additional external source to operate. It can be like inductor, capacitor, resistor that doesn't need external source to function. So in MMIC there is also a composition of passive components used. It is designed for impedance matching, DC biasing, phase shifting, filtering, and many other functions. This section presents a description of the passive components used in MMIC design. So talking about inductor, the microstrip ribbon inductor has an inductance limited to less than 1 nanohenry due to its DC carrying capacity and narrow track, which is controlled by the fabrication company. It is often used in distributed amplifiers. The microstrip layout, you can see the current circuit for inductor, capacitor, the MMIC capacitor, which has a higher capacitor per unit area, and the inter-digit capacitor can be used in MMIC. This capacitor is composed of two metal plates separated by a dielectric material. Especially the dielectric material overlaps the first metal layer, and the upper metal layer has a smaller area than the lower metal layer. This configuration helps to minimize the fringing effect of the field to the ground and source between the upper and lower capacitor, like as shown in figure. Resistor are used for feedback circuits, setting the bias point of active devices, isolation and termination for combinator and coupler. Two types of resistor are used in MMIC fabrication, including thin film of hallucinators and lightly doped gallium arsenide active layer transmission lines and weight gaps can be defined as device used to guide energy from one point to another from the source to the load. Transmission line can consist of a set of inductors, dielectrics, or combination. However, the transmission line are almost necessarily microstrip for MMIC purpose. Although coupler work at transmission line have been used as long, the characteristics impedance of the microstrip is inversely proportional to the ratio of the conductor width to the substrate thickness and also the dielectric constant of the substrate. Talking about combinators and dividers. Combiners are used to combine two or more transmission lines into one transmission line, and they also can be used to divide the microwave signal from one transmission line into two or more transmission lines. Microwave signal can be combined or divided by using T connections of two transmission lines into another transmission line. You can see in the diagram. The first one is the branch line coupler, and the second one is the ring coupler. You can see the different node, and they just get attached. attach and separate it. Another one is isolators and circulators. An isolator allows the microwave signal to pass in one direction but not in the other, which can be achieved by using ferrites. The ferrite metal is mounted inside the waveguide and the external magnet fixed by placing C-shaped permanent magnet and touch the ferrite. The isolation characteristics are the most important specification. However, a circulator routes the microwave signal from one port of the device to another. You can see the figure. The first one is circulator and the second one is isolator. The basic configuration of the circulator and isolator. And also another one diode are used in microelectronics to connect different material in integrated circuits, but also can be used to electrically connect both sides of a silicon wafer. These so-called through holes or diode can be used in a broad range of applications such as 3-dimensional packaging, 3D packaging, microelectromechanical system, MIMS, or multi-chip stacks, and both microstrip and backside grounded co-planar waveguide technologies. You can see the figure. Ideal case we are holding the gallery arsenic structure. Here bridge or crossover are required for most emergency layers, and here bridge is simply a metallic bridge that permits two transversal electric cross over each other without the formation of an electrical source of it. The ear bridge shown in figure. You can see this is the metal bridge and this is the aluminum structure. Wire bonding and bond pairs. Interconnection is necessary between elements and is accomplished by wire bonding. Bond pairs are provided to allow wire bonding for electrical connection. Additionally, through the wire bonding and bond pair, DC paths can be supplied and the output signal can be taken out. However, in the process of wire bonding, serious consequences can arise due to their low pass characteristics as shown in figure. You can see the first one is wire bonding, where chip 1 and chip 2 are interconnected through bond pair. Bond wire that plays the role of electron with parasitic resistance. And second one is split chip.